Hey everyone, welcome back to the channel Code with AKJ. Today is day 44 of solving LeetCode 75 challenge and we are tackling a classic graph problem, that is number of provinces. So if you want to keep up with the entire challenge and boost your DSA prep, make sure to subscribe to the channel for daily updates and fresh problem explanations. So let's get started. So the problem statement says there are n cities, some of them are connected while some are not. So if city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. So a province is a group of directly or indirectly connected cities and no other cities outside of the group. You are given an n cross n matrix is connected, where is connected of I and j is equals to 1 if the ith city and the jth city are directly connected, and is connected ij is equals to 0 otherwise. So we need to return the total number of provinces. So let's understand the problem. So we are given a matrix is connected where is connected of I and j is equals to 1 means city I is directly connected to city j. A province is a group of directly or indirectly connected cities and our task is to count the number of provinces present in this matrix. So let's see what actually a province is with the help of these two examples. So here I have drawn the two examples, both in the graphical representation and in our matrix representation. So we are given a matrix n cross n is connected. So here is connected of I and j. If it is equals to 1, it means I is directly connected to j and j is directly connected to I. So for this given example, we can see here is 1 is connected to 1, that is it is self connected, as well as 1 is connected to 2, that is why the value is 1. So if the value is 1, it means this particular I and j is directly connected. Since the value is 1, it means the city 1 is connected to city 2. So hence this particular representation. And we can observe here is, since the value is 0, 1 is not connected to 3. That is why there is no edge between 1 and 3. Same goes with 2. So here city 2 and 1 is connected. So hence there is an edge between these two cities. 2 is connected to itself and 2 is not connected to 3. Hence there is no edge between these two cities. So when we try to see the city 3 connected to which of the cities, so since the values are 0 to the cities 1 and 2, there is no edge between 3 and 1 and 3 and 2, and 3 is connected to 3 itself, so the value is 1. Based on this matrix representation, we have drawn this graphical representation. So coming to the example 2, we can observe that the city is connected to itself, hence the values are 1, and I and j both are equal. And we can observe that the values are 0 when we try to connect with other cities. That is why there are no edges between any of the cities. Province is a group of directly or indirectly connected cities. So here we can see that the city 1 is connected with city 2. So we can consider this whole single province, and we can consider 3 as a separate province. So for the example 1, we can say that we have 2 provinces here. Coming to the example 2, since there are no directly or indirectly connected cities, we can say that there are 3 different provinces and we'll return 3 as an answer for this given example 2. So this was all about the problem statement. So let's get started with our approach. So the intuition here for this problem is, it is essentially a graph traversal problem. So we can think of each city as a node, and if is connected of ij is 1, it means there is an edge between node I and node j. So the number of provinces equals to number of connected components in this undirected graph. So to find out the number of provinces, we need to find the number of connected components in this given graph. So that would be possible by using DFS traversal, that is depth first search. So let's see how this DFS works in this given problem. So we'll use DFS to explore all the connected cities starting from each unvisited city. So we'll keep a visited array. So the size of this array would be the size of our matrix, that is 3. Initially all will be marked as false, which means all the cities are unvisited at first. And second step here would be to start a DFS for every unvisited node. So since we are considering each and every city as a node, so we'll call a DFS function from each and every unvisited node. So first we'll start the DFS function from our first unvisited node. So in DFS, we will visit all directly and indirectly connected cities, and every DFS call from an unvisited node will give us a new province. So now here's an important part. Why does each DFS call from an unvisited city means one new province? So let's try to break it down. So when we start a DFS from a city that hasn't been visited yet, so from that particular city we'll explore all the cities that are directly or indirectly connected to it. This means we are visiting the entire group of connected cities, which is exactly what a province is. So once we finish that particular DFS call, all the cities that are in that province are marked as visited. So for example, if we start a DFS call from city 1 which is not visited initially, and this particular DFS call from this city would mark all the cities which are connected to it as true. So the DFS call from the starting node 1 would also make the city node 2 as visited. So since 2 is also connected to 1 and it is present in the same province, we'll be counting as a single province here. So after finishing this DFS call, if we try to start the next call from the city 2, and since it is already visited, we'll ignore that call and we'll move on to the next call. And here, since the another call would be from an unvisited city, so here we'll consider another province. So if we start a DFS from another unvisited city, it means it wasn't connected to the previous one, so it belongs to a completely different province. Hence, the number of DFS call from an unvisited city would give us a new province, and ultimately after every DFS call we'll make a count variable which would track the number of province present in graph, and finally we'll return that count variable. So that would be our intuition and the approach for this given problem statement. So let's do a dry run on these two examples, and let's also take another example where we can see that a city is being directly or indirectly connected to it. So since we have understood the problem approach, which is each DFS call from an unvisited node means that I have found a new group of connected cities, which means a new province. So let's do a quick dry run on these two examples and see how each and every step of our approach works. So our first step would be to initialize a vector of bool which would be the size of our number of cities and would be marked as false, which means unvisited. And we'll start a DFS call from a starting node, and for every call which is started from an unvisited node, we'll try to increment our count variable. So we'll also take a count variable which would be initially 0. And in our DFS function, our first step here would be to mark our current city as true. So we have started our DFS call from city 1 here, so we'll mark it as true, which means it has visited. And our second step here would be to run a loop over our connected size, and we'll check its connected cities. Since we have marked this as true, we'll also check with other cities as well, as we can see from this given graph, and we'll check whether this one is connected with other cities or not. Is connected of this node and I, which are 2 and 3, is equal to 1, and it is not visited. So is visited should be false, and city node and I should be connected. So if these two cases are true, then we'll again call our DFS function and mark it as true. So since 1 is connected to 2 and the value is 1 and it is not visited initially, we have called a DFS function again and marked it as 2. And this is included in our first DFS function call itself. And finally, when we compare this 1 with 3, since the value is 0, we'll stop that DFS function and we'll increment our count variable. So we have completed our first DFS function and we got our value as 1. Now again, our another DFS function call would be starting from 2, comparing the values with other cities. And since 2 is already visited, which means it is already considered in previous province, so we'll neglect this part and we'll again move to the next iteration. So now here, since 3 is not visited, we'll call a new DFS function, which means we have started a new province, and we'll now run a loop again. We'll compare with other values whether it is connected to other city or not. So here we can see that it is not connected to 1 or 2. So first our step would be to mark it as true, which means it has visited. And since it is not connected to other cities and it is a single province, will increment our count variable. So count is updated from 1 to 2. So in this way we have completed our DFS function calls for each and every city in our undirected graph, and finally return the count value, which is 2. So for this given example, our answer would be 2. So let's do a try run for the second example here, 1, 2 and 3. So our first step here would be to create a visited array. The size of our matrix, that is 3, and initially all of the cities are marked as false. So we'll start a DFS function from our first unvisited city. So here that would be 1. So we'll call a DFS function, and in our DFS function our first step would be to mark that particular city as visited. So we'll mark from false to true, and our second step here would be to check whether this current city is connected to any other cities or not with the help of a for loop, where we'll also check the two conditions, that is if this particular current city is connected to other city has a value 1 in our is connected matrix or not. So is connected of node 1 of 2 is 1 or not, to continue our DFS function. So since 1 to 2 is 0, we'll stop our DFS call, we'll return back from our function, and we'll again start a new DFS call from our second city. As of now our count is 1, and since we are starting a new DFS function, we'll increment our count variable from 1 to 2, and again our first step in our DFS function would be to mark our current city as visited. So false becomes true, and we'll check whether this particular city is connected to other city directly or indirectly or not with the help of our is connected matrix. So to continue our DFS call from this particular current city, to ensure that these two conditions becomes true, which is connected of this current city with other cities should be 1. You can see that 2 is not connected to 1 since the value is 0, and since the value is also 0 for the city 3, so we can say that 2 is not connected to any other city. So we'll return from our DFS call, and we can say that this city is a single city, which means a separate province. So since our count remains 2, we'll start a new DFS call from our 2 unvisited city, that is 3. So in our DFS function, our first step here would be to mark it as true, which means we have visited this city, and our second step here would be to check whether this city is connected to any other city directly or indirectly or not. So we can see that from our is connected matrix that the values are 0, that is connected of node with I is 0 to any other city, that is 1 and 2. So we can say that it is not connected to any other cities, means it is a separate province. So our count becomes from 2 to 3. We will stop our DFS calls as we have visited each and every city, and for each and every city we have called a new DFS call, which means we have 3 different provinces for this example. So for our example 2, our answer would be 3. So here I have also taken a separate example which is of size 4, which means we have 4 cities. Connected matrix representation is this, and the graphical representation is this. So we'll also do a dry run on this given example. So again we'll create a visited array. The size of the visited array would be the number of cities present in our graph, which means 4, and all the cities are unvisited initially, and we'll start a DFS call from an unvisited value, which is 1, and we'll also take a count variable which would be initially 0. In our DFS function, our first step here would be to mark this current city as true, which means we have visited this city, and our second step here would be to check if this city is directly or indirectly connected to any other city or not. From our is connected matrix representation, we can see that city 1 is connected to city 2, the city 1 is also connected to city 3, as the value of 1 to 2 is 1 and 1 to 3 is 1, which means 1 is connected to 2 and 1 is connected to 3 as well. So we'll continue that DFS function, and we'll continue visiting from 1 to 2 and 1 to 3. So while visiting these values which are directly connected to city 1, we'll mark it as true in our visited vector. So in this way, in our first DFS function, we have visited city 1, city 2 and city 3. We have also marked those cities as true in our visited vector. So our first DFS function call is completed, and we'll increment our count variable from 0 to 1. So we'll start a new DFS call for the second city. So the second city is already visited, which means it is already included in our previous province. So we'll move on to the next city. So a new DFS call and since 3 is already visited, which means 3 is already included in our previous province, so we'll neglect that city as well. So a new DFS call from an unvisited city, which means we are starting a new province. We'll give a DFS call, and in our DFS function, our first step here would be to mark our current city as true, which means we have visited this city, and we'll check whether this city is directly or indirectly connected to any other city or not. And from the is connected matrix, we can see that it is not connected to any other city, which means it is a single city and probably a single province. So since we have started a DFS call from an unvisited city, so we'll increment our count variable from 1 to 2, which means this is a separate province. So for this given example, the number of provinces are 2. So this would be our approach. So let's quickly move to the time and space complexity. So the time complexity here would be O of n square in worst case, as the matrix has n cross n entries, and in the worst case the DFS call may explore all the n neighbors for each and every n nodes. So we traverse each edge once in this adjacency matrix. So in the worst case, the time complexity would be O of n square, where n is the number of cities. Whereas coming to the space complexity would be O of n, as we are using the external data structure visited array of size n, and the recursive stack can contain all the number of cities in its memory. So that would be the time and space complexity of this approach. So let's quickly code this approach and let's submit. Let's quickly code our approach. So our first step here would be to calculate the size of our is connected vector, which means the number of cities present in our matrix. The second step would be to create a vector of bool of visited of size the number of cities, and initially all are marked as false, which means they have not visited yet. Our third step would be to declare a count variable, which is the number of provinces, which would be initially 0, and we'll loop with the help of for loop till all the number of cities, and we'll only call a DFS function if the current city is not visited, which means if visited of I is false, that is if not of visited of I, then we'll give a DFS function call sending the city, sending the is connected matrix, and also sending our visited vector. And for every new call of DFS function, we'll increment our provinces count, and finally we'll return our provinces count at the end. So let's quickly write our DFS function. So it would be void, it contains arguments as node, it takes adjacency matrix, is connected, and it also takes vector of bool of visited. So our first step here would be to mark our current city as true, which means we have visited this current city, and we'll run a loop till the connected dot size, and we'll check two conditions. If the current city is connected with other city, which means it has the value 1 and it is not visited. So if these two conditions satisfy, we'll continue our DFS function by sending this current city, that is j, and sending is connected vector and visited vector. So in this way our DFS function works. So let's quickly run this code. It's working, so let's submit. As you can see, this gives us successful submission passing all the test cases, and the time complexity of this approach would be O of n square, and the space complexity of this approach would be O of n. And that wraps up today's problem, that is day 44 of solving LeetCode 75 challenge using a clean and intuitive DFS based approach. So since this problem is part of the graph section of the LeetCode 75 challenge, we focused only on DFS traversal to count the connected components or the provinces. But there is another approach using something called union find or disjoint set union. But don't worry, that's a concept we'll cover in a future video once we get deeper into graph and greedy algorithms. So if you found this explanation helpful, make sure to give it a thumbs up and subscribe to the channel for daily coding challenges and clear concept breakdowns. So this was day 44 of LeetCode 75, and I'll see you in the next one. Until then, happy coding and keep learning. Thank you.